Earth's core is the planet's hidden heart, a region that challenges our imagination and technological limits. Even though we've never physically reached it, modern science has managed to uncover many of its secrets through indirect observation, especially by studying seismic waves produced by earthquakes. We know the Earth's core is divided into two main parts: the outer core, a liquid layer made mostly of iron and nickel, and the inner core, a solid sphere with a radius of about 1,220 kilometers. This inner core is composed primarily of crystallized iron under extreme pressure, millions of times higher than at the surface, and temperatures hotter than the surface of the Sun itself. Despite being inaccessible, scientists have been able to estimate its size, shape, and composition. The inner core makes up roughly 1% of Earth's total volume and is slightly flattened, with a polar radius just a few kilometers shorter than the equatorial radius. Seismic waves traveling through the core reveal remarkable anisotropy. They move faster from north to south than in the equatorial plane, pointing to a complex internal structure aligned with Earth's axis. Decades of research have refined our image of the core, ruling out the idea that it is perfectly uniform. Today, we know its dynamics influence many processes on Earth, from the magnetic field that shields life to the flow of heat driving plate tectonics. Still, Earth's core holds unsolved mysteries. How did we discover its existence? And what techniques allowed us to peer into its depths? We'll explore that in the next segment. For centuries, humanity could only imagine what was hidden beneath the Earth's surface. It wasn't until the 20th century that science found a way to see beyond what is visible and uncover the Earth's core. But how did we discover what lies thousands of kilometers below our feet without digging a single meter? The answer lies in studying the seismic waves generated by earthquakes. Every time the Earth shakes, these waves travel through its interior and behave differently depending on whether they pass through solid or liquid materials. Thanks to the Danish seismologist Inge Lehmann, in 1936, one of geology's greatest secrets was revealed. By analyzing how certain seismic waves reflected and changed direction at the planet's center, she deduced the existence of a solid inner core, surrounded by a liquid outer core. This breakthrough transformed our understanding of the planet and paved the way for decades of new research. From that moment on, scientists improved seismograph technology and developed models that allow us to see inside the Earth without the need to dig. By analyzing seismic data, conducting laboratory experiments, and studying meteorites, researchers have been able to deduce not only the existence of the core, but also its composition and properties. Today, we know that the core is essential for life on Earth, but its history and true nature remain mysterious. What is it really made of? In the next segment, we'll explore the core's composition and how iron and nickel form the heart of our planet. When we picture the center of the Earth, we imagine an unreachable world, full of mystery and raw energy. Yet thanks to science, we have managed to unravel part of its deepest secret, the composition of the core. The Earth's core is, above all, a metallic sphere made mainly of iron and nickel. It is estimated that about 70% of its mass is iron, while nickel accounts for between 4% and 10%. This unique blend of metals not only gives the core its incredible density, but is also essential for other vital phenomena on our planet. But how do we know this if no one has ever drilled all the way down? Scientists study metallic meteorites, remnants from the very materials that formed the Earth. These meteorites, called siderites, are composed almost entirely of iron and nickel. Additionally, the behavior of seismic waves traveling through the planet reveals differences in density and composition that can only be explained by the presence of these metals. Iron, the heaviest element produced in stellar fusion, sank to the center when the Earth was young and hot. Nickel naturally combines with iron, helping form a stable and resilient alloy. Although abundant, these precise proportions help the core strike a balance between solidity and fluidity, enabling phenomena like the Earth's magnetic field. However, the most accurate measurements suggest that small amounts of lighter elements, such as sulfur and oxygen, are present too, helping fine-tune the core's overall density. This interplay between heavy and light elements defines not only the core's physical structure, but also directly influences essential processes for life. In the next segment, we'll discover how this composition allows the core to generate the magnetic field that shields everything we know. Now that we know the composition of Earth's core, a crucial question arises. How does this hidden heart of iron and nickel influence life on the surface? The answer lies in the phenomenon of the magnetic field. The outer core, made of constantly moving liquid metals, generates a powerful magnetic field around our planet. This invisible field, known as the magnetosphere, acts as a protective shield that stretches thousands of kilometers into space. Thanks to this shield, Earth is protected from charged particles and radiation coming from the sun and deep space. Without the magnetic field, solar winds would strike our atmosphere directly, slowly eroding it and allowing harmful radiation to reach the surface. This would endanger both living beings and the technological systems we rely on every day. The magnetic field is also essential for the orientation of many species, from migratory birds to sea turtles, and for human navigation as well. Compasses, satellites, and global positioning systems all depend on the stability of this field. However, the magnetic field is not unchanging. Over time, it has varied and even reversed its polarity, phenomena that scientists study to understand their impact on life and technology. Studying this natural shield not only helps us understand how life is protected on Earth, but also offers clues about the habitability of other planets. But what is really happening in the core that keeps this field alive? In the next segment, we'll explore the secrets of its extreme temperature and how it shapes our planet's inner dynamics. Deep within our planet, Earth's core holds one of science's most challenging secrets: its extreme temperature. Although no one has ever reached the core, technological advances and laboratory experiments allow us to estimate that the inner core might reach temperatures close to 5,700 degrees Celsius, similar to the surface of the Sun. The outer core, which surrounds the inner core, remains liquid at temperatures between 4,000 and 5,000 degrees, under pressures so immense that iron and nickel behave in almost unimaginable ways. But why is the core so hot? The heat that remains is a relic from Earth's violent beginnings, when collisions and extreme compression released vast amounts of energy. Much of that original heat is still trapped inside. Additionally, the radioactive decay of elements like uranium and thorium generates extra energy, and the gradual solidification of iron in the inner core releases latent heat, fueling the process from within. The core's extreme temperatures not only stretch our imagination, but also affect how iron behaves, drive the formation of Earth's magnetic field, and influence geothermal activity. Yet, these estimated values are not final. Every step forward, through seismic observations or computer simulations, brings us closer to a more precise understanding, but also uncovers new questions about the thermal limits and inner dynamics of our planet. Many mysteries remain unsolved. How do we know so much about something we have never seen or touched? The answer lies in seismic waves, which let us read Earth's interior like a hidden code. That's what we'll explore in the next segment. So far, we've explored what we think we know about Earth's core, its composition, and its vital role for life. But how can we uncover the secrets of something we've never seen or touched directly? The answer lies in seismic waves. Whenever a major earthquake strikes, Earth vibrates like a giant bell. These vibrations, known as seismic waves, travel through the entire planet. As they pass through different layers, their speed changes, they bend, and sometimes they even disappear, depending on whether the material is solid or liquid. Scientists have learned to interpret these patterns. For example, S waves, which can only move through solids, stop when they reach the outer core, showing that this region is liquid. P waves, which travel through both solids and liquids, slow down sharply upon entering the core and change again as they cross the solid inner core. By comparing the arrival times of these waves at seismic stations around the world, researchers have mapped not just the size and shape of the core, but also details about its composition and inner dynamics. Even small differences in wave speeds in different directions reveal that the inner core isn't perfectly uniform, but rather has a unique and complex structure. Thanks to seismology, we now know that the inner core is slightly flattened, and that waves travel faster from north to south than from east to west, offering clues about the alignment of its crystals. Yet these discoveries raise more questions. What would happen if the core stopped spinning? In the next segment, we'll explore the consequences of this fascinating scenario. Have you ever wondered what would happen if Earth's core stopped spinning? Although it sounds like pure science fiction, exploring this scenario helps us understand the deep connection between our planet's inner engine and life on its surface. Earth's inner core is like a solid sphere of iron and nickel, floating within a liquid outer core. Its constant motion generates the planet's magnetic field, an invisible shield that protects us from solar winds and dangerous cosmic particles. If the core were to stop spinning completely, the magnetic field would weaken quickly. Without this shield, solar radiation could reach the surface, changing the atmosphere and threatening life as we know it. The climate could become more extreme, and sea levels might shift in unexpected ways. The length of days would also be affected. The core's rotation is linked to Earth's overall spin. If the core stopped, we could notice small changes in the duration of day and night, which could disrupt biological rhythms in living creatures. The core helps stabilize Earth's shape and its gravitational field. Without its spin, deformations could appear on the surface, and tides might behave differently. While these scenarios are hypothetical and current science suggests the core would never stop suddenly, imagining them makes us appreciate the delicate machinery that sustains life on our planet. But what if the inner core were very different from what we believe? That question leads us to a new mystery we'll explore in the next segment. As we venture deeper toward Earth's center, we find that the inner core, once thought to be a simple, uniform sphere, may hide even more complexity than we imagined. Recent research reveals that this solid region, made mostly of iron and nickel, is not completely uniform. In its deepest part, some scientists have identified an even more central sphere, an innermost inner core, with properties distinct from the rest of the core. This sphere, about 650 kilometers in radius, appears to have a different structure and a unique way of interacting with seismic waves. Waves traveling through it move at different speeds depending on their direction, suggesting a special texture and alignment of iron crystals. Its reactions to earthquakes also differ from those of the traditional inner core, puzzling experts and raising new questions about its origin. Some studies suggest that this innermost inner core could result from at least two separate stages of cooling and solidification in Earth's history, leaving distinct patterns in the iron structure. Others propose that thermal convection in this central region has nearly ceased, making it even more different from the rest of the core. These theories show that the heart of our planet is far more complex than once believed and are crucial to understanding how Earth's magnetic field and internal dynamics have evolved. But how do scientists study something so inaccessible? In the next segment, we'll explore the ingenious experiments and techniques developed to investigate the planet's hidden center. So far, we've uncovered the secrets of Earth's core, its composition, temperature, and essential role in protecting life. But how special is Earth's core compared to those of other planets in our solar system? Rocky planets like Mercury, Venus, Earth, and Mars each have internal cores, yet their properties differ greatly. Mercury has an enormous metallic core, making it unexpectedly dense for its size. Venus has a structure similar to Earth, but its lack of a significant magnetic field points to crucial differences in core dynamics. Mars, on the other hand, has a much smaller and cooler core, and its magnetic field is nearly gone, leaving its surface exposed to solar winds. Gas giants such as Jupiter and Saturn feature even more complex interiors. Their cores are likely composed of rock and ice, surrounded by vast layers of hydrogen and helium. The pressure and temperature inside these planets far exceed anything found on Earth, and their massive magnetic fields are driven by rapid rotation and conductive materials within. Uranus and Neptune, the ice giants, have small rocky cores and mantles where ices behave as hot, dense fluids, showcasing a remarkable diversity of internal structures. Comparing Earth's core with those of other planets helps us better understand not only our own world, but also the processes that shape the entire solar system. But if we can't travel to these hidden cores, how do scientists study them? The answer lies ahead in the next segment. Although we have never drilled more than a few kilometers beneath the surface, humanity has devised ingenious experiments to uncover the secrets of Earth's core. Since scientists cannot directly access the center of our planet, they rely on advanced lab simulations and cutting-edge technology to reproduce the extreme pressure and temperature conditions found deep inside Earth. For example, diamond anvils and powerful lasers are used to compress and heat tiny samples of iron to millions of atmospheres and thousands of degrees Celsius. These techniques reveal how iron behaves under such conditions, offering insights into the structure and composition of the core. To determine if the iron is solid, liquid, or partially melted, researchers use X-rays to observe its crystalline structure and estimate the exact temperature at the planet's center. Researchers also conduct experiments based on seismic waves. By analyzing how earthquake-generated waves travel through the planet and change as they pass through different layers, geophysicists build detailed models of the core, identifying solid and liquid regions and uncovering possible internal movements. Computer simulations are another essential tool. Using artificial intelligence, scientists create atomic-scale environments and predict how materials behave under conditions impossible to reach on Earth. These models help us understand the dynamics and evolution of the core, as well as its impact on Earth's magnetic field. Finally, experiments in geochemistry analyze the presence of light elements, such as oxygen and silicon, which affect the density and behavior of the deepest layers. All these experiments bring us ever closer to understanding the heart of our planet. Yet many questions remain, and advances in technology promise exciting new discoveries. If you love science and want to keep exploring Earth's deepest mysteries, subscribe and share this series so more people can join the journey.